Hi, everybody. Welcome and thank you for joining us this morning. This morning, Precisionary Instruments is honored to welcome Dr. Terence Wang, who will be giving a webinar on his use and customization of a Compresstome tissue slicer. So we're very excited to have him. So Dr. Wang received his degrees from the University of Hong Kong. He then studied biomedical engineering at Washington University in St. Louis and medical engineering at California Institute of Technology, or Caltech, for his Ph.D. degree. And right after his Ph.D. graduation, he went on to join the Hong Kong University of Science and Technology as an assistant professor, which is very impressive. And he's a professor in the Department of Chemical and Biological Engineering. He is also, if he hasn't done enough already, he also serves as a director of the Hong Kong University of Science and Technology Research Center for Medical Imaging and Analysis. His research focuses on developing smart optical and photoacoustic devices to enable label-free and high-speed histological imaging, as well as three-dimensional whole organ imaging, and you'll see some of that in his talk today, and also low-cost cancer targeting deep tissue imaging, which is great. He's an author or co-author of over 50 publications in top peer-reviewed journals, including many from the Nature Publishing Group, as well as conference papers and book chapters, and he also holds 5 US patents. So Dr. Wang, I want to hand it over to you, and thank you so much for joining us today.
All right, so thank you, Abby, for the very, very kind introductions. So good morning, everyone. So although my time zone is actually now at the nighttime, but I believe most of you are having your breakfast or morning time in your time zone. So thanks for having me today. So this is Terence, and I believe I don't need to introduce myself further. And today we will go through the journey about histopathology. For sure, we will have some part of it, the usage of the Compresstome, help us to bring the histopathology from 2-dimensional to the 3-dimensional part. So let's get started. So for the outline of this presentation, so I'll briefly talk about some medical problems that's happening in histopathology. So, and I believe may not all of you know what does it mean by histopathology. So the first part of it also mention about what does it mean to you. And then we'll come up with some sort of solutions, including to the histopathology. And then the first solution that we're going to propose, that is also a very key technologies being developed from my laboratories at UST, HKUST now. It's called computational high throughput autofluorescence microscopy by pattern illuminations. And we also leverage the power of deep learning to do some sort of virtual staining that I will also talk about in the later on part of these presentations. And followed by also what Abby have already introduced, we all do some sort of like 3D whole organ imaging with the help of the Compresstome and from the Precisionary instruments. And then we develop a very important technologies in our lab. It's called translational rapid ultraviolet surface excitations. So in short, we call TRUST. So then bringing together this TRUST system, then will naturally later on also incorporate the deep learning based virtual staining, bring us to 3D histopathology at the very end. So everything is connected, starting from 2D, 3D with the Compresstome, finally reaching 3D histopathology. At the end, I'll draw a summary. All right, so let's get started. So for histopathology, for those who may not know, so this histological or histopathological image, like these pink and purplish colored images, are those images that pathologists will view or will see under the microscope after slicing a very, very thin sections of biological tissues under microscopes. So the function of those images are very, very intuitive. You basically use them to classify different types of diseases, such as cancers. And you can also try to track the presence or also stage the cancers accordingly. So at the end, what's the outcome? Then you can guide the medical doctors to provide the best treatment for the patients at the right time point. So then what's the problem of the current clinical practice in the intraoperative settings? That means during surgeries, and also in the post-operative surgery. That means after post-operative use, that means after surgeries. So during the intraoperative settings, because it's time sensitive, it's really in a rush, we have to go for a suboptimal choice called frozen section. Why I call it is suboptimal? Although it's relatively fast, like 30 minutes, but then it provides relatively low and inconsistent image quality. And not only that, it requires very heavy, laborious sample preparation procedures and very complicated steps to make everything happen. So it's fast, but inaccurate. Vice versa, if you go for a relatively slow approach, what we term it as FFPE, formally fixed paraffin embedding. And this is really the gold standard. People provide the best images, just like the one at the top here, these two, extracted from FFPE. It is really very slow. So it roughly take around a few days, or not to mention it could reach a week. But then what's the advantage of it is obviously providing very high and also consistent image quality for different types of organs. So it's very useful, but again, it's still very laborious. So what conclusively, what are the problems in histological imaging then? So there are no such an imaging technology that can rapidly provide doctors high resolution or high quality visualization of the tissue structures with cellular level clearance. Okay, so very hard to do that. And the second thing is it's still destructive to the tissue and also very laborious, so such that at the end we can get those so-called high quality images. Okay, so very destructive and takes time. At the very end, like the frozen section, is not applicable to all types of organs. So collectively, if there is one technology that can serve this purpose, that means it can be time efficient, can be fairly simple, and also for all types of organs, that would be revolutionary in the histopathology domain. Okay, so what is exactly the problem that if we don't have the best technology that we have talked about so far? So just look at this cancer margin analysis medical problem in practice. So taking the States, United States as an example, 60 to 75% of the cancer patient, like breast cancer patient, were treated with conserving surgeries. What does it mean? They just try their very best to harvest, to excise the problematic cancer cells out from your body, and try their also very best to preserve the normal cells inside your body. Okay, so just remove the problematic cells. But then you can see the dilemma. So when you cut let's say the blue dashed line here, when you cut this mass out from your body, you may end up with the story on the right. So story on the right, it means that after the surgical cut, there's still some remaining cancer cells inside your body. Okay, so this is really what people don't want to see. This is also what we call positive margins. We want negative margins. But then what's the numbers of having positive margins is around 1 out of 5 patients, 1/5. 20% of the patients undergoing these conserving surgeries actually requires second surgeries due to positive surgical margins, due to the case on the right. And not even worse, what even worse is they only know after a week after the surgery. Okay, so that means that after the surgery, the patient is done, go home, and then finally they have to receive a call back saying that, sorry, I did not do a very good cut last time, so please come back for resurgeries. So very troublemaking, really causes a lot of anxiety for the patients, not to mention that the resources for the healthcare systems is not fully utilized because they just have to repeat the surgeries without contributing anything to the patients. Okay, so obviously we need a better diagnostic tool, but how come we cannot solve this problem for now? Okay, so then we go back to those FFPE and also frozen section. So in the operating room, we cut the tissue, we go through the first glance of the tissue by frozen section, just 30 minutes, you get a result. If we see that likely would be positive margins, they have to have another cut. Okay, just 30 minutes, we will have one round of this loop. But if you only when you see that is a negative margin, then the patient is good to go. Okay, so this can be a loop. And then what's the problem troublemaking is that the FFPE, some of the tissue will also go through that 1 week test, the FFPE following fixed parent embedding of the tissue. And this is really the resurgery call because the frozen section saying no, I mean, no cancer cells remain, so the patient happily going home. And the FFPE saying that, okay, sorry, that is still indeed some cancer cells remain in the cancer patients. So please come back for second surgeries. So what is the problem of this frozen section is indeed a very lengthy process. So we ask ourselves, is it possible? Okay, if we want to revolutionize the histopathology domain, is it possible to bypass all these steps? Because it's still 30-minute steps. It's not very fast, although it's the fastest process now already. So we ask ourselves, is it possible? So intuitively, it would be something like this. We excise the tissue out from our body, shine it with some sort of lasers or light sources. At the end, we can reconstruct some very high resolution that histopathologists can understand at the very end. Okay, so then we revisit most of the current thick tissue imaging techniques. So why I said that it's thick tissue imaging techniques, because you just can allow the surgeon to harvest some tissue from the patient body, and then we have to image the tissue directly. Can we bypass all the steps, right? We harvest the tissue, image them, and finally, hopefully generate images that is comparable to the pink and purplish colors that is provided by FFPE sample preparation steps. So all three here, like laser scanning confocal microscopy, photoacoustic microscopy, that is indeed my work, and also nonlinear microscopy, all these three seems very exciting, provide very, very similar images as the H&E stain, I mean the histological images. So as you can compare these two and also these images, fairly similar, but the drawbacks of these sets of methods it's label free, very, very, very fast in the sample preparation consideration, but the imaging speed is fairly slow. It's mainly because it's point scanning mechanisms. And another category is indeed fairly fast in terms of the imaging method is wide field. I believe many of you may know light sheet fluorescence microscopy, structural illumination microscopy, or recently relatively new is called microscopy with ultraviolet surface excitations. And all these three are wide field, much faster, but then the drawback is they rely on exogenous fluorescence labeling. So the sample preparation steps get longer. So we ask ourselves, is it possible to have both advantages? So label free, such that the sample preparation is fast, or I can even say that no sample preparation is needed. And not only that, we want wide field, such that we can provide very fast imaging, very high imaging speed. So that's really what we propose. It's called computational high throughput autofluorescence microscopy by pattern illumination. In short, we call it CHAP, by taking the first letter of most of the words of these technologies. So just go through a very rough picture of this technology first. It's that it doesn't really allow, doesn't need tissue slicing, because it can only image the superficial layer of the tissue, no matter how thick the tissue is. So it doesn't rely on any physical sectioning or even physical sectioning of the tissue. And not only that, we play with the intrinsic properties of the biological tissues. We really excite the biomolecules that provides naturally very high contrast between the cellular contrast, like the cell nucleus, and also cytoplasm, so that you can see the cells without real labels. And we also use pattern illumination such that we can enjoy large imaging field of view and also high resolution simultaneously that cannot be offered with traditional microscopy. And we also find out that when we do this, we really can relax also the requirement of tissue surface roughness. This is very important features that is surprising to us. Why is that? It's because structural illumination has been there, has been in the optical imaging domain for decades. But then not many of us are doing this for thick tissue. So when we do thick tissue, we see the really higher, even higher value of these key technologies is that when we do structural illumination, we use low magnification lens, that means low NA lenses to do that. So it will have naturally a relatively long depth of field. So this long depth of field will help us to be tolerating the surface roughness of the tissue. So as you can see in these images, the conventional method, we just use a high NA lens, maybe 0.25 NA lens, or even higher, such that you can see only this part of it is like in focus, but rather out of focus for the right part. Because we start with a low magnification lens, low NA lenses, such that it's less sensitive to this tissue surface roughness. It seems to us the tissue is completely flat, although it's the same. Okay, but it seems to us it's more flat. So, and structure illumination, I believe many of you may know. So just very, very quick recap. So basically we try to use structure illuminations to increase the imaging resolution by moderating some high frequency signals into low frequency passband of the imaging system. At the end, we synthesize a larger synthetic apertures, at the end also giving us a high resolution. So collect high frequency signals that is beyond the original detection limit of the imaging systems. And also for sure, we need to reconstruct our images. We are collecting 36 images, and at the end provide much higher resolution as you can compare these two. So the improvement of the resolution is about 2.6 times. And this is a very user-driven applications because we're targeting the histopathology, right? So our users are mainly pathologists. So as you can see previously, what I showed so far, these CHAM images are what we call grayscale images. So nice, but then it's not very colorful. So for the pathologists, they are very used to colors. There is more than a habit is that they thought that the color embed information for them to make a diagnosis. For example, they see very, very dense purple color. It may mean that there are many nucleus there. So maybe there's a very abnormal growth of cells. It already indicates the presence of tumor, for example. So the color is very, very important, although the structure is already very similar. So in order to make this hurdle even less for the pathologists, we even incorporate a deep learning algorithms such that to learn the differences between the grayscale and the ground truth H&E that is prepared by the FFPE, by the way. So it's the highest standard that we are comparing to. And the middle column here really shows you our results. So this is what we call a virtually stained deep CHAM images. So I believe it is really hard for you to tell what are the differences between the two. That's really the goal of the whole process. It's a user-driven applications or needs, I would say. So that is an easy adaptation by surgeons and pathologists, and eventually really improve the current clinical workflow. So, but then this virtual staining algorithm is also very fancy. There are many different types of algorithms. So one of the algorithms that we first employ or deploy is called supervised learning CycleGAN. So this GAN model really transforms the grayscale images, a grayscale CHAM image, to H&E stain image using a deep learning algorithm, and is bidirectional. So we can have a forward cycle and also have a backward cycle. And by optimizing all those loss functions, at the end, we can have these transformation fairly stable and also mimicking the real H&E staining. But then why we use unsupervised learning is because distortions always occurs in thin slices preparation. In the other words, if we want to prepare the grayscale CHAM image compared with the H&E stain images, during this sample preparation, because we start with the imaging a thick tissue, right? And then we try to image a thick tissue and compare with a thin tissue, the orientation may change. So there could be some distortion. Not only mention that if we play with thin slices may not be a problem. So this is very important because unsupervised learning allows us to not having any precise image registration. You can see these two sets of images are actually very different. So the CHAM image here and the real input H&E look very distinctive in terms of structures. They are not even, in a nearby region. So that's very important. So unlike supervised learning, you have to have them exactly paired, pixel by pixels. So as I mentioned, supervised learning is really not an ideal tool or not even an option for thick tissue learning to a thin tissue staining algorithms. All right, so let's go through some data that we can show. So the leftmost is a CHAM image, the middle one is deep CHAM, and the rightmost is a FFP-H&E. So by showing you, by the way, so it's very clear that we can see those like the interface between tumor and normal. And we go through some zoomings. I think you are convinced that they are fairly similar, like the normal area, those area structures in the, this is a lung cancer, by the way. So in the lung organ, you can see the airway structure is very similar between deep CHAM and also FFPE. Not to mention the cancerous region, like the large cell carcinoma, adenocarcinoma can also be observed. Much larger cell in the middle and also the bottom right part. And the top left is smaller cells accordingly. So it's very useful for the pathologist to classify different, the grade, the tumor, and also classify the subtypes of tumor by looking at this type of high quality histopathology images. So then we also image some thick tissue. By the way, the last slide is some thin tissue to gain some trust from this technology. And we also showed you that thick tissue. As I mentioned, thick tissue and thin tissue are different. So the deep CHAM image is imaging some thick tissue, and we try our very best to find the relatively similar orientation when we have a cut and prepare the FFPH&E. So again, by seeing the zoom-ins, I think you are also convinced that the structures, although they are not exactly the same as I mentioned, is because it's indeed slightly different in terms of orientations and thickness, but then you can still remarkably similar structures when compared with the deep CHAM and FFPH&E. So our pathologists also show that it's like minimal training or even no training can understand the images without causing any trouble in terms of diagnosis. So then we go further, for example, like not only lung tumor, we also try like breast tumor, and it turns out it doesn't go very well. So that's research, right? So we hope that it's going well, but it doesn't. So why it doesn't? So let me show you the result. As I mentioned, for thin slice, by the way, here is thin slices. Even for thin slices, if we use supervised learning, it doesn't go very well. This is kind of surprising to us. And then supervised learning, yeah, guess what? Supervised learning, if it's not doing very well as well, then supervised learning is like no hope. Okay, and we found that, wow, it really needs a much better algorithms. And why is that? Is because when we see very, very complicated structures and island structures and not enough training, that is commonly happening in deep learning, right? So when they don't learn enough structures, it doesn't go very well. That's one belief from us. And we also find another problem is the thin slices tissue distortions, such that the supervised learning also doesn't go very well. So we found out that, wow, we really have to have a better algorithms being developed by ourselves, because this might be the problem that we are experiencing, but not the others. Okay, so that's why we try to leverage the fact that we do have some similar images, but may not be the same image pixel by pixel, because the tissue indeed distorted during the sample preparations. So that's why we propose, instead of like perfectly supervised or purely unsupervised, we try to see whether something in between can happen and try to improve the overall performance. So we propose a weakly supervised deep generative model for complex image restorations. I want to really emphasize for complex image restoration, because for easy tissue structures, it seems the CycleGAN goes very well. But for complicated structures, and it doesn't. So that's why we really have to have a separate technologies or algorithm to address this kind of issue. Then really require less data alignment, and also, but at the end also provide much higher accuracies. So as a side note, this technology indeed is very, very powerful. Why I say so is because it's not only for like virtual staining, it's also for like although it's also some sort of virtual staining, but it's like predicting the fluorescence emissions from these kind of images. So from unlabeled images, bright field, phase contrast, we can also use this recrest. This method is called recrest, and compare with ground truth, that is even more superior than that of provided by the pix-to-pix. That means the fully supervised learning. Okay, so this is very, very encouraging. And we also try different types of data sets, but as for the interest of time, probably I'll skip. So the take-home message here is that it's really powerful. It even provides better performance than like supervised learning with different types of GAN model. All right, so let's come back to our human breast data that we used previously, using like supervised and supervised learning doesn't go very well. So what's the outcome when we use this weakly supervised approach? Let's see it. All right, so this is the one that we are showing. Okay, so if you're not trusting that it's fairly similar, let me show you some zoom in to really saying that this is like remarkably similar and also really providing superior performance than that of the pix-to-pix or CycleGAN. So CycleGAN is then supervised, pix-to-pix is supervised, and request is a weakly supervised approach. Okay, so rightmost is the ground truth here. So you can see these two are like fairly similar in terms of the overall structures, and also only the request is being able to outline there are two sets of cell types here. Okay, this area, the cells actually larger is the tumor cells, and the nearby area is like the lymphocytes. But the pix-to-pix is unable to classify that two types of two types of cells, and not to mention also this area lots of like lymphocytes are missing here, and also the case for CycleGAN, so not fairly stable. So really showing the powerfulness of request. That's a qualitative measures, and we also have some quantitative measure like SSIM or p-signal to noise ratio, p-signal to PSNR. So qualitatively and quantitatively, this is really also showing the best performance throughout. All right, so after knowing that, wow, it's really doing well. So we also demonstrated it's not only for lung or for breast, and we also check like whether it's powerful or usable for lymph node cancers. So this is again a CHAM, the request, virtually stained images, and comparative ground truth FFP H&E. So, and the zoom-ins, hopefully again, without saying any words from me, you are convinced that these two are very, very similar. Basically, it's very hard to tell the differences between the two data sets here. All right, so what's the final goal of the whole process? Hopefully I can have a quick recap here, is that in the future, we want to have in the operating room, we harvest the tissue out, we put it in what we call CHAM microscopes. So we want to have a commercial part of it, such that we can really bring from the lab to the clinical settings and save a lot of patients' life by reducing the number of surgeries or quick check of quick tissue biopsies in practice. So it will be a quick, simple, accurate cellular imaging tools. At the end, the pathologist can also remotely check the data without sitting in the operating room as well. And the whole process, when compared with frozen section, we try to compress the time from 30 minutes to just 3 minutes. And accuracies can be boosted up from 65 to more than 90%. That is what we are thinking of. So where we were at now, so we are pretty much fortunate to have lots of collaborators in Hong Kong hospitals to support us to get quite a lot of data. So in a few years, 2 to 3 years ago, we finished a lot of animal samples, and past 2 years, we have tried many different types of human organs samples also collected from Hong Kong. And the image similarities can be reaching 95%, as I showed just now, is the request, virtually stained images, or if it's not that difficult, maybe CycleGAN can also handle. When compared with ground truth FFPE, the similarities can be as high as 95%. So what's next is go multi-center, because having everything in one center doesn't mean anything. We want to make sure it's very reliable, very stable, and we also want to push the case numbers to reach a much bigger numbers such that people really trust throughout. And we also select that these top 7 organs that we want to try out, including lung, breast, prostate, liver, colorectum, colorectum, kidney, and skins, etc. Right, so indeed, we do have quite a lot of press coverage regarding this work. So we are so fortunate to have different interviews by the press, by different newspapers, journals, and to talk about this work. So that's enough for 2D histopathology, I guess. So let's switch gear a bit to talk about, as an imaging scientist, we always dream about having better performance. Is it possible to do 2D? And if so, where can we generalize it for 3D? Okay, so we want to see if it's possible or whether it's needed also to move from 2D histopathology to 3D. So then we see what's the current challenge in 3D examination of biological tissue first with very high resolution. It's very, very impactful, obviously, because of maybe fundamental science studies, improve the understanding of disease-induced structural changes, or the signaling between different pathways. So in 3D is always so value added to different research field. But it's so challenging to do, or there are many ways to do. So collectively, what is the common ground for people in science or people in the medical domain to talk is perhaps 3D histopathology. So currently 2D histopathology will undersample the biological tissue though. So I mean, we harvest a big tissue from the body, during the sample preparation or even in the 2D histopathology, we cannot image the whole thing. We just harvest a piece of it, and you may undersample the original biological tissues and causing some optimal call for surgical treatment. So, and also one problem in the 3D histopathology currently is that they try to get a thin slice first, and then image it, and then another image, try to image another thin slice, image another thin slice subsequently. And then at the end, they try to stack the whole thing. And you know, every time you cut, you can cause some destruction of the tissue. I mean, you may break it, like the tissue rupture in here. And you can also introduce some orientation or angular changes, such that at the end it's almost impossible, no matter what is the registration algorithm you tried out, it's still some imperfection in the 3D stacked whole organ imaging. So we ask ourselves, is it also possible to have distortion-free 3D histological imaging somehow be achievable? So then we visit the current large volume, high resolution bioimaging techniques. The first one for sure would be the oldest technology, like really doing it brute force. Okay, so we slice it, image it, slice it, image it. At the end, we stack it, just like the one I told you. And this is, again, as I mentioned, for the acoustic microscopy, I've been working this for quite some time. So this is from me. So point scanning mechanisms is good, but then it's just not fast enough for handling very large tissues. And there are many more, like two-photon microscopy, confocal microscopy, faster lasers, but then still point scanning, and not to mention it in general require tissue pre-staining. So making the whole process not very fast. And also we could have wide field methods like light sheet microscopy and some sort of tissue clearing. It is indeed a very hot field now. But just we also dream about using wide field and also some sort of real-time staining such that we can enjoy fast and also minimal sample preparation steps. This is what we dream about. So why do we have these so many, as I currently going through with you, is that we do have different applications, and so we develop different tasks, different tools for different tasks. So in general, we are balancing these four. I mean, image quality, imaging speed, sample preparation time, and also system cost. Okay, if we don't mind to have the highest image quality, likely maybe two photon or confocal is the best, and imaging speed, then you have to go for wide field, etc. So which one you prioritize the most likely will change your system design. Okay, so also another extreme is, okay, let's say my lab is so poor, then we have to stick with some methods that doesn't need lasers, for example. Okay, so all these have to take into account. So as I mentioned now here, one of the main consideration in my field or in my goal is to have very fast, so that we want to have wide field, and we also want to have very minimal sample preparation. If we dream about is like preparation free. Okay, fairly much like the 2D histopathology. We want to borrow that idea to see if we can do something very easily achievable, and in terms of system design, cost, and also speed. Okay. So, and as I mentioned, in terms of imaging speed, PM is fairly slow. Muse is fairly fast because wide field, and also light sheet is fairly fast. So wide field illumination is really one of the advantages that we want to enjoy. And sample preparation, as I mentioned, there could be some pre-labeling, pre-staining. Tissue clearing takes relatively long time, although there are many people in the field trying to wash the tissue in a much shorter time already. So, but still, we dream about to have a staining or sample preparation to be fairly minimal. So we want to have like, is it possible to do real-time staining? Okay, so that means I immerse the tissue inside a tank that with a lot of stains, and stain and during the imaging process. Okay, so that's what we dream about. And also in the terms of system cost, there for sure, as I mentioned, there could be many system considerations. You can use lasers, where if you use fluorescence, you may need PMT, and you may use fast scanning, then you need DMT as well. So this is what we don't want. I mean, we want to have very simple systems, maybe if not better, we want to have like just a LED with a standard camera. That would be the best. While we can still do this 3D whole organ imaging. Okay, we want to enjoy all these. Okay. All right, so that's really what we propose. This is a system called, or a technology that is proposed by us called TRUST, Translational Rapid Ultraviolet Surface Excitations. So why we call it translation? Because it's really low cost. We have like only LED as the excitation light sources, and because it's wide field, borrowing the idea of Muse. So so we don't really have to do real optical sectioning. The optical sectioning is really by the excitation, also the surface staining of the tissue during this staining process. So so if you can look into details, you can see that tissue is embedded inside a by the way, this is a Compresstome from the Precisionary instrument. So we basically just incorporate our microscopes on top of it. Okay, so you can see the tissue is embedded in the tank, and the tank is not water. The tank is the staining solution, full of staining solutions. So this staining solution, when it's not bind with the tissue, there's no fluorescence, and also no background fluorescence, I mean. So once it's bind, and then we will start having the fluorescence being emitted or excited by the excitation UV light. So I want to emphasize the one key thing about it is the steps. So we normally have to stain them in real time. Around 150 seconds, we can finish the staining and then start scanning. So scanning will take some time, and then after imaging that surface, we will shave it off. So it's called sectioning. And then after shaving it off the previously imaged tissue, a new layer will be exposed. So it will be a loop. Okay, new layer exposed, stain it again, image it again, slice it again. So why I will say that is a very important steps here is reversing the process of normal 3D histopathology in the case that I just mentioned. So in 3D histopathology, normally people do sectioning first, and then they image. So that's why the tissue is never intact. It's ruptured or have different orientations, etc., or some sort of like rotation problem. But then if it's imaged then first, when it's still intact, and then you shave it off, and then image another intact surface, you always have a very nice integrity or vitality of the entire tissue. So at the end, you don't need to do any registration of the image. You just stack them. You're really simply stacking them. This is indeed the final image that we achieved or we got from these systems by imaging and shaping it up, this process repeatedly. Okay, so I also want to give credits to this very cute waterproof case design. So we want to minimize the pathway for the light being traveled in the staining solutions, because although this is having very minimal fluorescence, but after passing through this very long journey, this part here, you still have some relatively weak fluorescence. It's kind of degrading the overall contrast. So here is showing you with or without the waterproof case. So without, you can imagine that is completely immersed in the objective. The objective lens is completely immersed into the staining solution, and if not, the tank. Okay, so the this one is very important to make high contrast and high image quality happening for TRUST system. So here is a very short video showing in practice, in action, what is happening. Yeah, so you can see after shaving off the surface layer, there is a suction here. We'll collect the shaved off slices. So at the end, after collecting, we can also do whatever processing we want. For example, we want to still prepare the ordinary H&E stain, etc. So up to us. Okay, so this is the VF700 OZ version or model of the Precisionary Compresstome. So the real-time staining, I also want to give some more credit about this staining process about a single or double labeling. So we only use PI previously, showing, wow, we can see the cells, but the contrast somehow is just not good enough. So when we do like DAPI and PI stain together, the neuronal structures is more obvious, and the layer structures, some of the cells is more distinctive, and just the overall contrast just be better. Okay, so here also want to give credit for this part. And so it's also important to compare different systems about like tissue preparation steps, whether how easy it is, how lengthy it is, or whether it's point scanning, image speed, etc., cost effectiveness, blah, blah, blah. So I believe the trust system, I'm not saying that we provide the very best image quality. I never claim so, but then it's really a nice interplay or balance between image quality, imaging speed, and cost effectiveness. Okay, so this is the table summarizing those 3 points that I want to mention. All right, so really going through some image gallery journey of this trust system, as I mentioned, is really, I want to show the powerfulness of trust for whole organ imaging. So by the way, let me emphasize one more time. We never do any image registration. So we just image the surface layer, shape it up with the Compresstome, and then we stack another layer and keep doing it. And then at the end, we stack everything. And that's it. We got this kind of high quality 3D model of the mouse brain. So by seeing different cross section, coronal section can be also extracted. And here shows you a collection of zoom-in images. Different important features in the brain can be also, and the mouse brain can also be identified. And because it's RGB, I mean, the image is colored. So we also can play with different color channels and do some sort of data processing. We can also extract like blood vessel structures. At the end, we can also project them nicely with different ways. Okay. So another big part of it is we want to show how generalizable about these technologies. It's not only for brain. Okay, so we want to see that how many organs types can be also comprehend by these very important, and also at the same time fairly simple imaging systems with the help of the Compresstome. So we show that for heart muscles, heart organs, liver, kidney, lung, spleen, all do fairly well. So although the lung is the one that we do have to have some sort of treatment of the tissue, we may need to have the injected gelatin to support that in a better form, because there are just so many airspace in the lung tissue, making it so hard to cut very well. But then for other like heart, liver, kidney, spleen, all of them are doing very well. All right, so here's a video. Hope that is not too laggy, although I try to play it like this. It's a mouse brain project reconstruction model. So we can, after the reconstruction, we can simply play in different angles, see in different views, and then see different contrast later on as well. So here is the cell nucleus extracted from the hippocampus. All right, and with different contrasts, we also can extract the nerve tracts and myelin fibers. Right, that's enough for the brain. And as I mentioned, with different image processing approaches, we can also digitally extract the blood vessels. And we can could be injecting some sort of contrast agent into the brain to also improve the contrast accordingly. Okay, so this is a mouse kidney. This is a very interesting video. Previously showing you the outline, and now showing you the blood vessels network. And we also do segmentation to try to extract the glomerulus features in the kidney, such that each green balls here are each individual glomerulus. So showing a lot of features can be extracted from these systems. And also, for example, we have our own subsequent data processing skills here. Okay. All right. So instead of playing one by one, remaining other organs are playing them simultaneously, like liver, spleen, lung, and heart, and all shows very high image quality. And I'm just giving you collections of them simultaneously like this. Okay, so what's next? So we also try to see not only soft tissues. For sure, we cannot cut bones, but then for embryo, this bone is still very soft. So we try to see if we can cut the embryo when it's still intact. I mean, the entire embryo is put into the Compresstome, and then we try to cut it as well. So this is E15 and this is E18 embryo. So we try to cut the whole brain as well, or even later on cut the whole body as well. So we can see the developmental biology. I mean, for the purpose of developmental biology, we can use these as a very powerful tools to see some sort of structures development throughout different time point of the organs, etc. Of the species, etc. Okay, so here are some more zoom-ins, a cross section. We try our very best to find some close sections of the two different embryo. So E15 and E18, all these structures are showing you. We also check with some biology book, showing you that we are indeed extracting features that is highly aligned with the gold standard or the well-known structures. Okay, so what's the future or what's more we want to do is to bring this technology to have even faster features. I mean, even compress the time shorter, finishing the entire whole organ imaging scanning. So we want to learn the high spatial resolution from maybe lower resolution lenses, just maybe 4x magnification lens. And we have a 10x image. We try to learn these by pairing them up with deep learning. So such that at the end, this is what we call deep trust. So you can compare the image with the 10x. Some of them are close, but some of them even may be better because the 10x could be out of focus easily, relatively, because the depth of field in general is too sharp. Okay, showing that is very feasible and also very promising to speed up the whole process, and also at the same time provide maybe even better image quality at the very end. So finally, we touch upon the 2D histopathology, 3D whole organ imaging. Then let's talk about the 3D histopathology. So we build upon trust. This is still the trust system, but then we also incorporated virtual staining algorithm or tricks into trust, such that at the end, not only the colorful images for basic scientific discovery, we can also do it as a virtually stained H&E images. At the end, the people in the medical domain can also understand and appreciate. And here really shows you some references or I mean quick demonstrations. So the left column here is the trust image. The middle column here is the virtual trust. That means it's virtually stained by CycleGAN, the network. And the rightmost is the FFP H&E. Again, we remember the suction, right? So we indeed collect the tissue that is like sliced, shaved off. And you see they are also different though. I mean, although we are collecting it, some of the part is like ruptured or is indeed empty on that particular layer. So they are different, but then overall structures like the nuclear count or the distribution are very, very similar, showing the virtual trust is highly trustworthy. So here again, with the powerfulness of trust, naturally everything is aligned. I mean, the whole organ is naturally aligned without the needs of image registrations. You can use that directly, and then you can see the different layers, structures, and then different cuts. You can see different layers in different view angles, whatever, you can play with it. So as long as you have all the data with it. Okay, so something similar, we have also the mouse brain projections. So because they are indeed fairly similar, probably I don't want to drag longer for this part. And how about the next one then? So this mouse liver is an interesting video as well. So you can see that this virtually stained features with the zoom ins. Hopefully you're convinced that it really looks like a real H&E stain to you. But not only that, because of the other contrast, as I mentioned, we can also extract the blood vessels features on top of this H&E projection. So try to unifying the difference between scientific and also medical domains with the same platform. Yeah, this is really what we dream about. So something similar, without playing them one by one, now showing you a collection of it. All of them are virtually stained images with the CycleGAN model. So it's fairly easy to do and with different zoom ins, etc. Okay, so I think I have chat for quite some time. So in summary, I've shown you a 2D histopathology method. For the histopathology domain, 2D imaging method is called CHAMP, computational high throughput autofluorescence microscopy by pattern illumination. And we also have this deep learning favor for the virtual staining, such that to minimize the training that is needed for pathologists. So for intraoperative surgical margin analysis is one of the key applications that we have been addressing on. At the same time, after that, we also have introduced this 3D whole organ imaging with a Compresstome from the Precisionary instruments. So the system we propose is called TRUST. So we believe that it really serves as a backbone to realize 3D histopathology and also very favorable for basic science studies because it's fairly fast and cost effective. Not to mention the image quality is fairly high as well. So at the end, we combine everything. Okay, so we have the 3D whole organ imaging with the Compresstome. We also have the deep learning favor, the virtually stained tissue, such that we enable this 3D histopathology and make it feasible with I would say, relatively simple tricks. All right, with that, I actually would like to end here. So I would like to open the floor for questions. Feel free to ask any questions and I'll be here to answer them. Thank you.
Oh my gosh, thank you so much, Dr. Wang. Wonderful. So I want to open up the floor for questions. And if you want to unmute yourself, let me know in the chat box if you have a question, and then I'll call on you guys. So we actually have a question here from Gloria. She's asking, is there a commercially available system based on what you have shown us?
Wow. Okay.
Yeah, we wish it were. Yeah, that easy.
All right. So thanks for the question. So indeed, you probably can see the commercial value of this system and also maybe the entire a few projects. We indeed have the for the CHAMP, we're pushing the commercial part of it. So we are fairly close to real commercialization. So right now we have already a few different prototypes in different hospitals on site. So in the coming year or two, we will have like manufacturing them in larger scales, such that it will be commercially available. For the second part of it, the trust part, the commercial part, currently is not on our. I would say, I have to be honest, we haven't have a chance to really commercialize it. But if we do see lots of interest, I think there could be ways to maybe talk to work with Precisionary instruments to make that happen. Mm-hmm. Thanks for your questions.
That was great. And so we also have Mitch Shoiket asking, just commenting, fascinating work, Terence, asking, can you comment on the XYZ resolution of the 3D approach currently and also in the future?
That's indeed a very good question. So that's why the trust is so, let me go to the table.
Okay.
It should be close.
No worries.
All right, cool. Yeah, here you go. So this image, this table doesn't show the resolution. So that's why I think it's good to refer to this first. So currently the imaging systems of trust is fairly good in terms of like tissue preparation, imaging speed, ease of use, cost effectiveness. But what's the current drawback? So that's why I said it's a perfect question. Is that the XYZ resolution, in particular the Z-axis resolution, is not that good. Why I say so is particularly, for example, the tissue dependent and also the staining speed dependent. So that's why this is our first generation of trust. We cannot have full control of the Z resolutions. In general, what we find out is most of the tissue, our penetration depth of UV light excitation is around 30 micron. Is around 30 micron. So this will give us the actual resolution in the Z-axis. X and Y is not that bad. X and Y is around 1 micron resolution. It's mainly governed by the objective lens that we use. So that part is very okay. But then for the actual resolution improvement is actually our Trust 2.0. So we are working on that.
Wonderful. And I have Michael Jenkins has a question I just love. So
Sure.
Dr. Wang, what do you see as the most promising clinical applications for 3D histopathology?
Yeah, another great question again. So, you know, I have to admit that as engineers, we normally do things by reverse order. I mean, we are good at something, we've developed the best technologies, and we somehow omit or ignoring what's the needs, right? So that's why when we have the transition page, we ask ourselves whether it's needed. Okay. So one very common questions that we ask is whether it's needed, and in practice, this is one application that we have came across that we read some papers, is that in 2D, because you can only examine a few slices, and you may undersample the entire big features of it. Maybe from some slices, the tissue, the cancer size, a cancer cell size or cancer tissue size is not that big. And in particularly deeper layer, they may be bigger. It could be. At the end, if you miss the biggest layer of that cancer tissues, you may have a different call of surgical practice. So this is one applications in that domain. Another domain I would say is like checking for metastasis or more on the medical side research, but may not be during the operations you want to have an outcome of it, because it still takes some time, although I said it is fast than many methods, but it's still not to a point that you can get it in a second or with a click of a button. So I would say it's on the research side. Maybe transcriptomic, this is one also very hot field. You serve as a thick tissue image with the H&E contrast. You can also borrow the transcriptomic application to project what's the potential change of genetic sequence. That is also one very hot field that we are trying to investigate on.
Wonderful. Oh my gosh. Well, Dr. Wang, thank you so much for your time. I think that wraps up our webinar, and I want to make sure that we respect everybody's time as well. So thank you so much. We're going to give you a virtual round of applause.
Thank you.
And we will make this recording available online, and we'll send it out to all of our clients and scientists. So again, thank you very much. And I wish everybody a wonderful week.